If I had to make a commitment, I would say that stars are the most important objects in the universe. They make up larger objects such as galaxies. They are at the center of solar systems. The material from dead stars form new stars, so they're really part of the whole circle of life issue. So learning about stars is really an important aspect of learning about astronomy. And so when you learn about something, you learn about the properties of that something. So I'm going to go over some different star properties and just some ways that we know those things and some ways that different characteristics can be tied together. So first one is mass. Obviously you can't put a star on a scale. The best way to figure out the mass of a star independent of some other inference is by looking at stars that are in binary systems, their properties as they orbit each other. So here are two stars that orbit each other, or more precisely, a common center of mass. And here's just a graphic representation of that. So we've got, and this also works with planets orbiting stars as well, but it's difficult to see stars orbiting other planets. Just about 1% or so of all planets have been discovered by direct imaging. So here we've got two stars, and these are stars, and they each have their own brightness. So when they're side by side like this, you're going to have a certain brightness. When one of them passes in front of the other, we're going to see the full brightness of the one, but it's going to block part of the brightness of the other. And then it goes to the other side. So most of the time we see the two stars independent. And then we see the smaller star in volume go behind the larger star, so we don't see any of its light at all. And then we get this big dip. So the size of the dip, the duration of the dip, the duration between dips, all of those tell us about the orbital properties, which tell us about the mass. So another characteristic is luminosity. So we've got our star and AU. Remember, that's the standard distance between the Earth and the Sun. So light spreads out in all directions. So if you were to capture the light that spreads out over a 1 astronomical unit square here, and then take that to 2 astronomical units, that light has spread out over twice the length and twice the height. So it now covers 4 squares, which means each of those squares is just going to be 1/4 as bright. 3 AUs, it's going to cover 3 squares by 3 squares, or 9. Each one of those squares is going to be 1/9 as bright. So that's what's called a 1/r squared rule, or an inverse squared rule. As you increase the distance, the luminosity goes down by the inverse, the square of the inverse of how far you've gone out. So double the distance means 1/4 the luminosity. Spectra. If stars are the most important constituents of the universe, then spectra are the most important pieces of information. And there are 3 different types of spectra. There's a line spectra, there's a continuous spectra, or there are line spectra, continuous spectra, and absorption spectra. When we look at stars, we see their absorption spectra. So stars consist of a hot light source, so that's primarily the energy at the center. That energy passes through the outer layer of the star, which is cooler, so that's the cloud of cooler gas. And then if that light passes through a prism or a diffraction grating, it turns it into a rainbow, but the cloud of gas will absorb a few select wavelengths of light, and the select wavelengths that are absorbed relate to what's in the star itself. So when we look at this, an absorption spectrum, we're going to see the full rainbow with lines cut out. If we look at the intensity here, so this is peaking in the kind of the orange. So this would be for sort of a yellowish orange star, and then we'd have these intensities that drop down. So here's an example of the information we can get from spectra. And I'll talk a little bit more about these letters here. These are just different star classifications, different spectral types. But you can see they all have the general rainbow pattern, but the lines differ. And not only do the line patterns differ, so an M star is a small cool star, a red dwarf, and O is a large blue star. Not only do the line patterns change, but even the thickness of the lines. So you can see the hydrogen lines, for example, are pretty weak here in the O stars, pretty strong in the A stars. So looking at the absorption spectra, if you're on Wheel of Astronomy, like Wheel of Fortune, on Wheel of Fortune you buy a vowel. On Wheel of Astronomy you want to buy a spectrum because that tells you a lot. It can tell you the temperature by looking at the relative intensities of the colors and the pattern of the absorption lines. It can tell you the material in there as well. Here is your new friend, the HR diagram, named after Hertzsprung and Russell, the people that discovered it. So the HR diagram has an X and a Y axis. On the X axis is temperature, and there are these spectral classes again, O, B, A, F, G, K, M. The acronym OB affine gecko kiss me. That's the way to remember it, because who doesn't want to be kissed by a gecko? Notice it's a little bit odd in two different ways. One, it's logarithmic, meaning that the distance here in degrees between 3,000 and 6,000 is pretty big in terms of number of inches. Roughly the same number of inches here is the gap between 10 and 30,000. So that's called a logarithmic scale. Also notice that the high temperatures are on the left. The bigger numbers are on the left. Here's luminosity. This is another logarithmic scale. So look at here from 1 to 0.1, that's a difference of 0.9. Here from 1 to 10, that's a difference of 9. 10 to 100, a difference of 90, and so on. So the sun's located right here. It's a G2 star. So spectral class G2, and it's obviously as luminous as one sun. You can plot every star on this graph because every star has a temperature, every star has a luminosity. And if you did that, you'd notice some patterns. First off, you've noticed that most of the stars are along what's called the main sequence here, which is kind of a straight line that's a diagonal from very luminous and very hot to not very luminous and not very hot, so low temperature for a star. Our sun is sort of in the middle of this. There is more gap, there's more space on the main sequence above the sun, but there are many, many, many more stars on the main sequence below the sun. You would also notice, so most of the stars here, you'd notice that there's a family of stars here that are giant stars, so many times the radius of the sun, on the order of perhaps 10 times the radius of the sun. And you'd notice that there's a set of supergiant stars. Most of the giant stars are reddish and orange. Most of the supergiant stars are reddish and orange, with a few of them being blue. You would also notice, and these would be the last ones that you would notice, would be white dwarfs. And the reason you'd notice them last is because they're not very luminous. Look at them down here. The brightest white dwarf is maybe a tenth as luminous as the sun. They are high temperature, but they're very low luminosity, and some of them being extremely non-luminous. And by the way, luminous just means the amount of energy radiated. So white dwarfs don't radiate that much energy. Supergiants and giants radiate a lot of energy. So up here we have stars that are large in size, so large in radius and volume, low in temperature, very luminous. Upper left-hand corner, high in temperature, pretty large radius, although not as large as the supergiants, and very luminous. Down here we have stars that have a small radius, high temperature, not very luminous. And over here, small radius, although not as small as the white dwarfs. White dwarfs are about the size of the Earth. Red dwarfs are roughly the size, the radius of Jupiter, a little bit bigger, and definitely more massive. This is a very busy diagram. So I urge you to pause the video. I'll go over it, of course, but pause the video and look at it more closely. There's also a similar diagram in the textbook if pausing the video doesn't give you a very good resolution. So show some of the masses. Down here, these are stars that are on the order of 1/10 of a solar mass. Up here, we've got stars that are 10 to 100 times the mass of the sun. And here's the sun in the middle. These lines going across are solar radii. So the two example white dwarfs, Procyon b and Sirius b, and by the way, they're called B. Sirius was a star discovered in antiquity, as was Procyon, but not until fairly recently, the past 100 or 200 years, did people discover that those two stars weren't single stars, but they were stars that had a white dwarf companion. And here is the star Sirius right here. Here's Procyon. So they're both a little bit larger and a little bit brighter than our sun. This Sirius, this probably counts both Sirius A and B, but Sirius B doesn't contribute much to the size or the temperature or what you observe when you look at Sirius. If you look at Sirius and Procyon, even with a fairly large Earth-based telescope, you only see the main stars, which is now called Sirius A or Procyon A. And that's 10 to the minus 2 solar radii. That's 1/100th of the radius of the sun. That's about the Earth size. The Earth's about 1/100th the radius of the sun. Up here we've got 10 solar radii. So Spica in the constellation Virgo is about 10 solar radii. Pollux in Gemini is about 10 solar radii. Up here we're getting 10 to the 3rd, so about 1,000 times the radius of the sun, Betelgeuse. So this is just a great graphic in terms of how stars look and their temperature and their luminosity. Just a comparison of the sizes. So here's Betelgeuse, which is interesting. It says 500 solar radii. The diagram on the previous slide showed it at about 100, and I just looked it up on Wikipedia because somebody asked me a question about it, and it's on the order of 1,000. So 500, 1,000, it actually does vary. What I read, it varied from I think about 900 to 11 or 1,200 solar diameters. So large supergiants pulsate, they shrink and expand, so they're variable in brightness as well. So it would swallow up the orbits of the inner solar system planets, Mercury, Venus. I don't know why they didn't show Earth. Earth would be about here. Mars would be near the edge of it. Aldebaran is a giant star. So here's Aldebaran. Here's Betelgeuse. Aldebaran would fill a significant amount of Mercury's orbit, but not the whole orbit. And notice that Aldebaran here has been magnified 5 times. Magnify this by 10 times and we get the sun. So here's the sun right here smack dab on the main sequence. And then just a comparison with Earth and Procyon b, white dwarfs, about the same. Now the mass of the white dwarf is about the same as the mass of the sun, but its volume is about the same as the Earth. So just think of how dense it must be if you take the sun's mass basically and shrink it down to the size of the Earth. So remember, HR diagram, really important diagram. This is something that you should learn, be able to understand. Look at an HR diagram and understand everything it's telling you. Remember, it's your friend. Spectra, they are also your friends. Stars, of course, we know that stars are a friend. Thank you.